I would like to take this opportunity to tell you some of the ideas that are coming to the fore in terms of ways in which we might be able to control acid gas emissions and mitigate the harmful effects that they have on the global climate patterns and the like. It is well recognized that there have been significant temperature changes over the decades. This shows how things have varied over the US in the last century or so, with a dramatic increase in temperatures over the last couple of decades. And in fact, this past summer has seen some number of records that have been broken in terms of temperature rises around the western coast of the US and in Canada. But this is really not just a US problem, of course. It's a global problem. We have global warming, and this gives us a global warning because we are looking at the polar melting, wildfires, drought, ocean rise, superstorms, flooding, and various other kinds of negative effects of the global warming on the environment on the planet. This, of course, has been highlighted in the very recent IPCC report, in which says this is certainly a code red for humanity and really needs to be addressed very, very dramatically in the very near future. Well, the global temperature change it's been strongly correlated with the rise in carbon dioxide. It's a well-known correlation that the temperature rise of about a degree or so the past century has been associated with a rise of about a 30% rise in the carbon dioxide accumulation in the atmosphere. This has been known to give some significant negative climate effects, but it also has an impact on the oceans as well, in terms of pH and acidification of the ocean waters, with this dramatic effect on the marine life and on corals and the like. So this is a very serious problem, and it's going to be one that's going to get worse as time goes by. Unfortunately, we do need to, we are reliant on fossil fuels. The CO2 is produced, of course, from the combustion of fossil fuels, and we are reliant on fossil fuels to keep the wheels of industry churning for the time being. While we are looking at renewables, of course, that are coming into play, fossil fuels are going to be around for quite a while. And the emissions from the fossil fuels are around about 35 to 40 gigatons per year, which is pretty substantial. And if we go on business as usual, the emissions will continue to rise, and this will lead to a temperature rise of about 4 to 6 degrees minimum by the turn of the century, which is really unsustainable for human habitation as we know it today. So there is a very important, very dire need for us to be able to reduce these emissions and to keep them below 2 degrees, to keep the temperature rise to be below 2 degrees Celsius by the end of the century. We'll need to have this kind of a profile for the greenhouse gas emissions. And in fact, at some point, we're going to have to start putting CO2 out of the ambient environment as well. So not just a matter of mitigating the emissions themselves, but to actually sort of atone for our past transgressions by taking it out of the environment. So this region here, of course, is where we have to have the mitigation, and this can be done through a number of sources. One is transition to non-carbon sources for energy, of course, nuclear, renewable, etc., etc. But we can also look, and it's going to be a very important component of the whole mitigation strategy, is to look at carbon utilization and capture and utilization and storage. And so we're talking primarily here about stationary carbon dioxide emitters from various industrial sources and power sources and the like. And there needs to be a net removal of these CO2 with permanent storage in subsurface aquifers or in utilization in production of chemicals or building materials and the like. So, but there is an issue with the fact that not all of the CO2 sources can be mitigated in this way, and there are mobile emitters and agricultural activity that lead to also greenhouse gas emissions. So we have to sort of compensate for that in any strategy we might have in terms of CO2 emission strategy, and this would call for negative greenhouse gas emissions much earlier than originally anticipated, and in particular within the next 10 years or so, we really do need to start putting a very significant effect. We really start need a significant impact of the negative emissions on the total emission profile. So how do we go about capturing CO2? This really is going to be a very strong need for the capture side of CO2. And so what we've got to think about is the actual capture technologies that are available for us in this regard. And typically the source of CO2 we know are power, transportation, industry, and accumulation in the atmosphere. Storage of CO2 through sequestration, and value-added utilization, and then production of chemicals and fuels and building products and the like. In the meantime, what kind of capture technologies are there? Traditionally, the capture technologies have been temperature swing or pressure swing, in which CO2 is captured and then can be released in a concentrated form by increasing the temperature and releasing the CO2 or decreasing the pressure. These are both energy intensive and particularly the temperature swing processes require a significant amount of energy integration, and also in terms of, in many cases, you may not have ideal temperature sources for doing this. What we like to explore, though, is the idea of using electrochemical means in which we can exploit just renewable resources. We do not have to worry about the heat integration issues. We can just rely on electrochemistry to provide us the driving force and so on. So if we look at traditional sorption modes for CO2 capture and release, we have absorption and adsorption. In absorption, the CO2 is fed into, or the gas stream, feed stream, is fed to a absorber, an absorber, where they actually come into contact with a circulating liquid with which they interact. They can either be physically dissolved or they can be enhanced. The solution can be enhanced by chemical interactions with components in the sorbent itself. Once the sorbent is fully loaded with CO2, it can be taken to a desorber where we heat it up and drive off the CO2, break those chemical bonds, drive off the CO2 as a pure gas. Then the solution must be cooled down again to be recirculated back to the sorber. On the other hand, we have adsorption type processes in which the CO2 is actually physically absorbed or chemically absorbed onto the surfaces of packing particles within the bed. And then once the bed is fully saturated with the CO2, it's taken offline, and we can then regenerate it again by heating up or reducing the pressure in the system. Generally thermal processes here. Now both of these can be energy intensive, and what we like to do is explore other approaches we might be able to use for these kind of operations. Traditional sorbents for CO2 capture are shown here. There's a wide range of things that have been looked at, and they can be operated over a wide range of operating temperatures depending on the processes of interest. But these are fairly well, many of them are very well developed, and others are certainly still very much in the exploratory stage, but there's some very intriguing applications in these systems. But I want to focus on another set of technologies that we could look at, which do not rely on these temperature changes at all. In particular, I want to talk about electrochemically modulated CO2 capture, in which the capture and release of CO2 is going to be regulated by the oxidation state of the redox active species. So what we are relying on is modifying the actual interactions of various components with CO2 under different applied potentials. They can be regulated by applying different potentials as governed by the Nernst equation. There are two different approaches we can look at generally. There's a direct approach, which is shown here, in which you have a component, a species that will be reduced, and then this reduced species interacts very strongly with CO2, so the CO2 binds directly to the species of interest. And then when we're fully loaded, we can reverse it and oxidize the species to give us the Q back again and the pure CO2. The actual fraction of the species that is reduced is very strongly governed by the Nernst equation, in particular by the applied potential relative to the standard state potential of the redox group. So that we can recognize then that we can regulate this by going back and forth in terms of the voltage. Another approach is to look at the indirect approach, in which we would have some components, an amine, interacting with CO2 to give us a complex LCO2. That is not electrochemically active at all. But then we have a second species that can be oxidized to give us an A+, as shown here. When we throw that A+ in with the LCO2, what we find is that there's a strong displacement. The A+ is much more strongly favored by the L than the CO2. So it displaces the CO2 from this complex, and you then get the CO2 coming off as a pure gas again. And then, of course, the A+ can then be reduced to regenerate the L. That'll go back to give us other options for CO2 capture. Again, this is all governed by the Nernst equation, as shown here. Electrochemically modulated process for CO2 capture, there are a number of these that we can use. The one I'd like to talk about in particular are A and D in this thing. We've got the electrochemical generation of nucleophiles, in which case we got the what we've got is the quinone coming in. It's a quinone type molecule. It comes in here. It will be reduced at the cathode chamber, where it's also contacted with CO2 through gas diffusion electrodes in this case. And when we get the reduced quinone, it will react very strongly with the CO2 to form the biscarbonate, as shown here. This can then be taken to the anode side, where it is reoxidized, the quinones are reoxidized, and the CO2 is released, and we regenerate the sorbent. So this is a cycle in which we have a direct interaction. The same kind of systems can be used indirectly when we've got protic solvents. In this particular case, when we get the reduction of the quinone, it actually gets protonated rather than capturing the CO2. It captures the protons, and this really causes a decrease in the pH, an increase in the pH, and therefore an increase in the CO2 capacity to form a bicarbonate in this particular case. On the other hand, when this is reduced, the protons are released, the pH goes down, the capacity for the bicarb transformed back to carbonic acid, and the CO2 gets released in this particular case. A third case of interest is another indirect situation in which we've got an amine plus a carbon dioxide forming the amine carbon dioxide process, and we then feed that through to an anode chamber where we release copper ions. These copper ions will then displace the amine, displace the CO2 from the amines, so you get CO2 coming off. And then we can take the copper amine solution and send it back to the cathode chamber, where we reduce it, and the copper comes off, and we regenerate the amine. And we can have this kind of a cycle. I'm going to talk about these two cases in particular right now. So first, let's talk about the electrochemically mediated amine regeneration process. I hope to be able to show you that there's some significant advantages of this, and there could be some really energetic advantages as well as possibly economic advantages. Typically, we'd have an amine solution come into contact in the gas absorption column, an amine solution come into contact with the CO2 to form the carbamate, as traditionally done. And then what we want to do is be able to regenerate this in the desorber unit. But rather than doing this thermally by heating up, what we do is we take it into the anode chamber of the system, where we now add copper ions, the oxidation, add copper ions, and this will then complex with the amine and kick off the CO2. Once you've got that, we can then disengage the CO2 in the flash tank, and then the solution can be fed back to the cathode, which is done as amine copper complex. In the cathode chamber, what we do is we reduce the copper, and we then regenerate our amines, and the copper is plated out in the cathode electrode, and we can go through this complete cycle. This is actually a process we've done. We just spent a fair amount of time looking at it, and we have a bench scale unit that's been operating effectively for many hundreds of hours on and off. And this shows the overall unit. That's the electrochemical cell we have. It's about 10 centimeters, about 20 centimeters in size. We've got all sorts of other things here. We've got the absorption column, we have switching valves and things like that. And this has been used rather effectively over many cycles. This is 100 hours of operation, continuous operation. And what happens, of course, is that the anode dissolves, the cathode grows, and at some point we need to sort of reverse these, so the cathode becomes the anode and vice versa. So we need to reverse the potential and also switch the flows between the two chambers. But that is really readily done through switching valves and the like. This shows you the kind of results that we can get. In particular, what we're interested in is what is the gas output product. And you can see that generally we're getting around about 100% CO2 coming off our column in this regard. And the gas output rate is very close to theoretical gas output rate, which is really controlled by the current in itself. This is the applied current, and that determines the rate at which the CO2 is going to be released, because that determines the rate at which copper is released. And so then we get the cell potential as shown here. You can see this is still very well, these electrodes look pretty good after 100 hours of operation. They still look very clean and just looks like pure copper here. We don't get much contamination with other species on the electrodes. The thermodynamics are very interesting in the process, and we need to know the thermodynamics to be able to evaluate the overall energetics of the operation. Well, we've looked at the thermodynamics for the process, looking at all the reactions that can occur in the system, and then using traditional standard, thermal solution thermodynamic type correlations and approaches for looking at the system. The important part here is the actual potential, how the equilibrium potential varies with the activity of the copper ion in solution. So this is going to be an important consideration. But to be able to look at this, we need to know all the other reactions that are occurring as well. So you incorporate all of these in the overall place, and we can get a potential copper loading diagram is shown here. This is the potential that one would have and the equilibrium conditions as a function of a copper loading. In other words, how much current has passed through the system, how many charges have been transported. So copper loading is really a measure of the state of charge of the system. And what we've got, the blue lines are constant CO2 loading. In other words, that all the speciation of CO2, carbonates, bicarbonates, and dissolved CO2. The red lines are the constant fugacity. So this could be considered to be the system pressure, for instance, if you're looking at pure CO2 in the system. So what we can look at now is how does this, what is the thermodynamic cycle in this particular process? Well, if we look here, we've got at this particular point, we've got gas coming in. The copper load is only about 0.2. We've got gas that's in equilibrium with a fugacity of about 0.13, about 13% CO2. And we then begin to start passing current through the system. Copper gets released. CO2 then gets kicked off from the amines, and the concentration of free CO2, dissolved CO2, increases in here, just as pure CO2, carbonic acid. At some point, what we find is that then we get to a saturation level, and once we're at saturation at that particular pressure, fugacity, any additional CO2 released will come off as a gas, and we maintain at a constant pressure, or constant fugacity in the system. So then we get to the outside of the anode. We're at this particular point. The gas is released, and then we go take it back to the entrance to the cathode chamber, and then bring it back to the outside of the cathode and go into the column again. And this green is just the absorption in the column. So what we've got here then is the fact that the concentration, this is the relative concentration in equilibrium with the gas at that particular fugacity. And so we can see then we've got the constant, this line follows a constant concentration curve. This, of course, is a thermodynamic line, and we can look at the overall cycle, and we can calculate the minimum amount of work that's required to do this separation, and to find it's basically around about 15.6. So it's really just the integral of the potential over the current for the two legs of the oxidation and reduction cycles. I do want to point out that what we're interested in is how many electrons are required per CO2, or how many CO2s are released per electron. What you'll find is that initially it's not 100% because the initial electrons that are introduced in this region here are actually not being effectively used for releasing CO2 into the in the gas phase. It's because the CO2 is still retained in solution. So we don't expect to get really close to 100% Faradaic efficiency, but we can expect to get quite close to that. I do want to point out one of the things that one needs to be concerned about. Those are under equilibrium conditions, thermodynamic equilibrium conditions. But we need to think about what the actual overpotentials are to drive that reaction at a reasonable rate. And so if we now look instead of the system as shown there, we're interested in what the position is, what the variation in potential is as a function of the position along the cell. So our copper loading goes from 0 to 0.8 here, and on the cathode side from 0.8 to 0.2. So you can see we've got the two curves as shown here for the redox and the oxidation states. The particular potential applied would not follow these curves. It would just be a constant potential. You apply constant potential across the electrodes, along the whole position itself. So what we get is immediately see some inefficiencies here associated with the fact that we have the electrodes are at constant potential rather than varying potential depending on the concentrations. So what we've got to think about then is not only that, but we also have to rely on the fact that we need to drive this at a reasonable rate. So we need a stronger driving force, and this is why we have to apply overpotential as shown in the blue here, and this provides an added inefficiencies associated, or added energetic costs associated with the overall process. We can minimize or reduce this energetic cost by using segmented cells, as shown in this case here, in which only part of the electrodes at this potential, the other section of electrodes at this potential. So we can now reduce the energetic penalties somewhat by using segmented electrodes rather than one single electrode. And indeed, we'll find that here the actual ideal for this particular case would be 26 kilojoules rather than 15 kilojoules for the minimum case. The energetics of the amine system, they are similar to what we see in traditional MEA or thermal EDA, the thermal type processes. The interesting part in here is the EMAR process is the minimum work that's done for the electrochemical methods, and then we've got to worry about the overpotentials. And this is an area here where we might be able to get some significant advantages by clever design and engineering of the electrode systems themselves. The actual costs, a strong techno-economic analysis allowing for all sorts of inefficiency, other processes, indicates that we can between $40 to $45 per ton, depending on the actual membrane cost. It's determined significantly by the membrane cost itself. And the cost of electricity would be similar in terms of the for what you see in the MEA and other kinds of processes. But these were done early on. We've done some more work on this since then and recognized that by modifying the solution conditions and the like, that we can actually enhance the overall performance of these systems. And in particular, if you use mixed amine systems, the EDA, AEA, amino ethanol amine case, what we find is a 50-50 mixture, we can actually reduce the cell voltage required quite a bit, quite dramatically. So overpotentials are reduced, which is something we'd like, and the energy consumed is going to be significantly less as well. And so it's much less than the 40 kilojoules per mole. In addition, we can add surfactants to the system. We find that initially there were issues associated with the bubble formation, hindering the electrochemistry at the surface of the electrode and leading to actual particle formation in the anode chamber, which was rather unexpected. But by adding surfactants to the system, we can sort of reduce the bubble size, and we can modulate the overall electrochemistry at the surface of the electrode. And this can lead us to really clean, separated solutions of the gas and the amine solution, copper amine solution, as shown here. And this has led again to a significant reduction in the overall cell potential cell voltage and also in the energetics of the system. So we're down to, in this particular case, around about 27 kilojoules per mole, which is quite significantly lower than what you had before. So this shows there are some very strong indications that we can do a great job on improving performance. Now, I'd like to switch gears now and go into the other one. So that's just talking about the indirect approach. How about the direct approach? Well, there's been some work done in the past by others as well, but we've latched onto this and looking at the quinone type systems, in which quinone, as shown here in the dormant state, really has no affinity whatsoever. It just ignores the carbon dioxide that's around. However, when you reduce it, it gets very strong electronic density on the oxygens here, which provide a very good site for the electrophilic CO2 to be captured to form the biscarbonate, as shown in this particular case. So we capture the CO2 by the agent that's been electrochemically activated. Once this is fully loaded, we can now take it and oxidize it again to release the CO2 and regenerate the dormant quinone that can be used. Now, we've done some work in looking at this, a new type of approach, looking at electro-swing adsorption kind of operations, as opposed to having these quinones in solution. What we do is we take the quinones and we immobilize them on an electrode substrate. So this is the quinone immobilizing electrode substrate, because of anthraquinone in this particular case. And then we need a counter electrode to provide to be able to complete the circuit. In this case, we used a ferrocene counter electrode. We had this particular kind of configuration, and this whole thing is immersed, is bathed in ionic liquid electrolyte to provide the ionic current and be able to close the circuit. So what will happen is when we reduce the quinone, we'll be able to capture the CO2 as shown in this particular case, and the case here. And the same token, we oxidize the ferrocene to ferrocenium to provide the electrons for the reduction of the quinones. When you want to release the CO2, of course, you just reverse the potential. In this particular case, what we have is that on the oxidation, we get the CO2 being released, and the ferrocenium is now being reduced back to ferrocene. So that completes the overall electrochemical cycle. That's a complete cycle. Now let's just take a look and see what we need to do. Obviously, what we need here is the charge balancing. For every electron that goes to the anthraquinone, we need to take an electron from the ferrocene. So let's just take a look at this particular process. We can use this Nernst equation, which I discussed earlier, for the quinone system, and the charge concentration, in other words, how much of it actually is reduced, is given by an equation, this equation, and it's given by a curve that looks something like this. We will, for the time being, assume that this is equivalent to the CO2 concentration as well. So every charged quinone is bound to 2 CO2s, and we'll assume that this is a CO2 concentration. By the same token, we also have the counter electrode, which is the ferrocene type electrode, as shown here, and this would be the actual charge concentration in the ferrocene electrode as a function of potential relative to its redox standard redox potential there. Now what happens when you apply a voltage to the system, it has to sort of walk around and be able to satisfy charge balancing. So what we need then is, when you apply a voltage, so V capture, it means that we've got this difference then has to be met, and also we've got the charge that balances, the charges are balanced in these two systems. Then what we do, if we want to release the CO2, we can actually come down to a much lower voltage, as shown here, and this is the amount of CO2 would now be bound to the quinones relative to what was before during the capture stage. So obviously this is the amount of CO2 that is being released following capture in the system. So that is really the overall concept that we're going to follow. Now, the way in which you prepare these electrodes is quite straightforward. We take the polymer, in this case the ferrocene, but also the same for the polyanthraquinone. wrap it around carbon nanotubes and put them in a suitable solvent, and then use that solvent ink to either drop cast or dip coat a carbon fiber electrode substrates in the system. And you can see from very close up here that you can see the actual film that's formed is very, very porous. These are the carbon nanotubes here. They're coated with the polymer. Carbon nanotubes are really neat because they can provide strong electronic conductivity. They provide a high porosity to facilitate ionic conductivity. And there's a large surface area that's really accessible for the adsorbates to find places to go. This is gives an indication of the way in which we did the initial experiments. This gives you an indication of the electrode structure and how we assembled the electrodes. We put these in a sealed chamber with electrical contacts, of course, and the sealed chamber is connected to a pressure transducer. Introduce CO2 into the sealed chamber, and then when we apply the potential, reduction potential, the CO2 gets absorbed, the pressure goes down, and you can then calculate the number of moles absorbed, and then you can go back again. When you reverse the potential, you see the pressure should go back up again. Indeed, we can calculate the amount of CO2 captured from these fluctuations in the pressure, and this shows the type of charge. This is a reduction leg and then oxidation, the amount of charge applied, and this is the CO2 that's being captured and released. Well, that's captured on the reduction side and released on the oxidation side. And we can do this, and we've done this for many, many cycles. Typically with a grade about 90% Faradaic efficiency, and typical 40 to 50 kilojoules per mole of the overall energetics, which are quite favorable, actually. We can do better than that, though. This is another option, another way in which you can look at it is a flow system in which CO2 has come into gas diffusion electrodes, and we monitor the actual total CO2 that's coming out, and from the integral of the CO2 that's leaving here, we can estimate how much has been absorbed on the polyanthraquinone electrode. In this case, we used a different cathode electrode, lithium iron phosphate electrode here, all in an ionic liquid. An important part about this is that the capacity, overall working capacity of the system, did not vary over about 150 cycles, as shown here, and then our coulombic efficiency was really high in this particular case, close to 100% for the most part, which is really encouraging. Of course, that's not the way we're going to operate in a real-world situation. What we'd want to is have an adsorption bed, in which we have the electrodes in the bed, as shown here. This is a stack of electrochemical cells. We introduce the CO2 at a certain concentration on the feed side, and then as it passes through, the CO2 gets absorbed, and the gas leaving out here would essentially be depleted of CO2. As the bed gets filled up, this concentration front moves through the bed until eventually it gets to a point where the total bed is totally saturated, and you get the concentration begins to increase. You can see here what you've got, the normalized concentration, the outlet concentration, as a function of the inlet concentration. Let's look at this one here. You can see we're removing essentially all the CO2 in this particular case until about 10 bed volumes. That's the time over typical residence time. And then only then do we begin to see a breakthrough in this particular case. This is shows a very strong absorption capability for the beds. Now, the energy, the release voltage, the energetics, of course, are important. The energy is then given by the charge transfer divided by the Faradaic efficiency, and then the difference between the capture and the release voltages here. As we talked about before, this is the kind of thing we have. This is the CO2, bound CO2 concentration, and this is the capture and release voltages in the system. Now, if we get this release voltage, we have that amount of CO2 released. If we have a smaller delta V, in this particular case, we only have a smaller amount of CO2 released. So the smaller CO2 released, but also the energetics are going to be smaller as well. In fact, if we look at the fraction released, as shown here, as a function of the delta V in the system, we can see that this is what you would get as we decrease the delta V in the system. The good part about this, although we're getting less utilization of the total quinone in the system, we are actually getting much lower energetics per mole of CO2 released. So that's a really strong plus for this particular case. And here we're well below 40 kilojoules per mole. This can also be done in a continuous process if we wish, in which we have the, in this particular case, we have a cell, an electrochemical cell, in which we have the quinone solution flowing through here, ferrocene solution thrown, and we can do the oxidation of the ferrocene and the reduction of the quinone. The reduced quinone can then be taken to the absorber. We pick up the CO2, and then it can then go to a desorption unit. We do the oxidation of the compound and a reduction of the ferrocenium, as shown here in this particular cell, and then we can then disengage the CO2 that's released in a sweep stream. This case here, the ferrocene just goes around in this particular loop as a working fluid in this case. And we've shown that this works. There's still some work to be done to optimize it, but in particular this desorber flow, how much CO2 are we releasing? And we can show as a function of current in that desorption unit. As we increase the current, go from 0 current here to 15 milliamps, 25 milliamps, and back to 15 milliamps. We can see we can regulate rather well the actual rate of release of the CO2 in the system. The energetics aren't as favorable at this particular point. We're still pretty high, about 100, 150 kilojoules per mole, much higher than we'd like, but it's basically something we can work towards. Now that's all just showing the overall concept. We do need to think about negative emissions and look at direct air and ocean capture. And from an electrochemical perspective, these are still very, very new topics. And so I'd like to just go over some very preliminary results we've got in the system. The first is looking at the quinone system again. In this particular case, you've got the stack of cells as shown here, and the like. And what you do is we flow CO2 in and have a voltage applied, and then we release the voltage and release the CO2 and back and forth. And so, yeah. So we can actually get the captured CO2 is given by the integral in this curve, and this is a released. After a certain period of time, about 5 or 6 cycles, we start to level out, and we can see that we've got a very stable cyclic process. Again, the caloric efficiency, and this is for looking at ambient air conditions at 400 ppm. It's around about 95%, 90 to 95%, which is really very efficient. We'd also like to talk about direct ocean removal using electrochemical methods. Now, the thing is, the concentration of CO2 in the ocean is depend on the pH. You've got the carbonate, you've got bicarbonate amount of concentration, and you've got the CO2 in equilibrium, just a physically dissolved CO2. And this is a log scale. So you can see as we decrease the pH, what we're going to be doing is converting the more bicarb into a CO2, and that can then be released quite significantly. And so we've looked at ways in which we can do this. People are doing some work on looking at electrodialysis type approaches. We're looking at a slightly different approach that may be able to minimize some of the expenses there. In particular, what we have is a series of electrode systems. Feed the ocean water in here. We release protons by electrochemical activating, release protons from a certain type of electrodes. The protons are released and decrease the pH and release the CO2 that then gets released. We then take the solution back again and recapture those protons. So the protons themselves just going back and forth. And once this is depleted, the proton of this electrode depleted, we then sort of flow the solution, the seawater, to this electrode system. So again, it's a swing type operation. This is some preliminary results we've got using a certain set of electrodes when you release the protons in the CO2 release stage and capture the protons when you go back and realkalize the water and before it gets returned back to the ocean. These should be easily deployed. We can rely on renewables completely. We don't require certain things that other approaches seem to require, either ion exchange or bipolar membranes, a separate analyte and catholyte streams, addition of chemicals, or we don't require formation of byproducts or secondary streams in this case. Some of the preliminary results we show here are different current applications of current and different shows the regeneration step and the release step, and how it is certainly these cycles are pretty good. And we can show that we got removal rates are pretty respectable, around about 70-80% in general. The energetics are still a little high, but this is acceptable at this stage, and we know we can reduce these to some extent by better design of the electrodes and the flow patterns and the like. So where does all this energy come from? Well, we need carbon-free energy sources for negative emissions. We can rely on a distributed capture and release or a centralized release in which we capture all the CO2 in a solution and then just release it all at a centralized location. The capture rates would be on the order of 500 kilotons per year. CO2, the energy at about 1 to 4 kilojoules per ton, and the power would be about 15 to 60 megawatts. And this brings us to what kind of sources do we need? Well, we can use solar and we can use wind, of course. They do take up a lot of real estate. Or we could use some of the new ideas in terms of nuclear batteries. I know that colleague Jacopo Bongiorno is looking at something like this, in which you might be able to fit in a 5 to 10 megawatt unit into a container as shown here. So, well, these are fairly versatile. These Faradayically modulated electro-swing technologies can play a vital role in the mitigation of CO2 emissions. They're very versatile type approaches, and they're also applicable across multiple scales and concentrations. There are, of course, a lot of challenges we need. We need to know how to make these electrodes very effectively and cheaply. We need to have fundamental advances in materials chemistry to enhance the overall operations, and then we need to engineer the practical electrochemical systems and that. I do want to point out that this whole area of electrochemical technologies for CO2 capture is still in the fledgling stage. There is some interest now. It's suddenly growing in the last 2 to 3 years. The number of publications in this area has blossomed and bloomed, gone up about threefold in the last couple of years. So there's a growing interest in this area. And the DOE is also very, very interested in pushing these concepts. So with that, I'd like to acknowledge the work of the various students and postdocs in my group and also the funding agencies. If I can answer any questions, I'd be happy to do so. Thank you.